Hi, this is Mel again, and today we're gonna go through Chapter 17 about differentiation and anti-differentiation of polynomials. This is from Math Method Unit 1 and 2 of VCE subject. Okay, so today's summary is mainly about the diff and integral of polynomials and some algebra of limit and continuity. Okay, let's go through bit by bit. First, the derivative, the notation for the limit as h approach 0 is like this one. So the limit h approaches, the arrow represents approaches to 0, is represented like this. If approach to infinity, then we write like this: positive or negative infinity. So after the notation, we have for the graph y equal to fx, the gradient of the secant pq is given by this one. What does the gradient mean? So the gradient is the slope, the rate of increasing or decreasing of the function, right? So the gradient from p to q. Let's look at this graph over here. P we have x, fx, and q we have x plus h, f, x plus h. So it's clear that this part should be h. So this is x, this point is x, this point is x plus h, and there correspond y value. Okay, so the gradient is the delta y divided by delta x. So the f x plus h minus fx divided by the change in x, which is h. And this gives the gradient of secant pq. Then with this idea in our mind, we can relate with the limit we just learned about, which comes up with something like this. So if h approach to 0, so h is decreasing and decreasing until it's 0, so until it's a point. This actually represents the point on the red curve of the gradient. So as h approach to 0, very, very close to 0, so pq are very, very close together, and this represents a point on the red curve, which the gradient at this point actually represents the derivative, which you can see something over here. So the derivative of fx at any point, if h is close to 0, then we have the derivative with this function over here. So yeah, so the gradient at a point is equal to the derivative at a point. Okay, let's move on. At a point x, fx on the curve y equal to fx, the gradient is the derivative of x, which we just talked about. For the graph over here, the derivative of fx is larger than 0 for all x is smaller than a, and for all x is larger than b. Let's see. What is the derivative? Why do we want to compare the derivative of fx with 0? So if the derivative is larger than 0, that actually means, for the red part of the function, it actually means the graph is growing. It's growing. And for negative, so smaller than 0, which is the purple part over here. So this part, we have a decreasing function. And if it's equal to 0, we have the points, the point A and point B, which later on you'll see that are the stationary points. So the rules for differentiation. For constant, fx is equal to c. So if we draw a graph, we can see, for example, equal to a constant c. So y is equal to c. For example, c can be 1 or 27.3. It doesn't matter, but their diff is equal to 0. So their rate of increasing at all points are 0. You can see from this line over here, it's not increasing or decreasing. So it's flat, so it's 0. Even for fx is equal to 0, we also have the diff is equal to 0. Okay, that's for constant function. And what about polynomial? Fx is equal to the x power n. Then we have f dash is equal to n times n minus 1. So we take the n down, and then we minus the power by 1. For example, if we have, let's look at this one. If we have x cubed, then we take the 3 down, which becomes a constant in front of x, and then 3 minus 1 is equal to the power 2. That's for polynomial. And let's see, if we have a constant k in front of the gx, so we have a constant term in our function, then we can actually, when during differentiation, we can take the k out, so it does not affect the diff of the rest of the function. For example, we have 3x squared, then we actually can take the 3 out and then do the diff for x squared, which we take the 2 down, become a constant, and 2 minus 1 have power of 1. Okay. Then for this case, we have 2 functions adding up together. So how do we want to diff this function? We actually diff each of them, each of gx and hx, and then sum of them together. For example, this one, x squared plus x cubed. We diff each of them and then sum together. That becomes 2x plus 3x squared. Okay, that's about rules for differentiation. What about antiderivatives? So for antiderivatives, if we have big F dash is equal to fx, so that means the diff of big F is equal to small f, then reversely we can have the integration or the antiderivative of fx is equal to big F plus c. Don't forget the plus c when you integrate. Okay, where c is arbitrary real number, so it's a constant. If we have a polynomial, then we want to integrate the polynomial. What do we get? So as I said earlier, it's actually a reverse of diff. So if you want to prove this, we can actually take the right-hand side and then diff, you should be able to get this one, to get x to the power of n. Let's try together. So we have plus c. And above we said if we have 2 functions, then the diff of them should be the diff of each, then sum. So let's diff this one first. How do we want to diff it? We take the n plus 1 down. So we have this one, and then times x to the power of n plus 1, then minus 1. We minus 1 to the power. What about constant c? We said earlier the constant have diff of 0, so it's just plus 0. In the end, we get x power n, which is exactly this one. So it's very important to remember that integration and diff are reversely related. Okay, similar over here, if we have two functions f and g, we integrate both. We want to integrate the sum of two functions. It's actually equal to integrate of each of them and then sum together. And same for constant, we can take the k out and then do integration, where k is a real number. Okay, so now about algebra of limit. So some rule about limit. Limit is actually very closely related to differentiation. So if we want to take the limit of the sum of f and g, it's actually same as taking the limit to each of them and then sum together. Keep in mind that the a is still the same. Or you can say the limit of the sum is the sum of the limit. And if you have k, which is similar to previous cases, you can take the k out. K is a real number. And if you have multiplication of two functions, you can actually separate them and then take the limit of each. Or you can say the limit of the product is a product of the limit. Same for division. If you have fx on gx, then you want to take the limit. It's actually the same as taking them separately and then divide them. Important to know that the denominator will never be 0. You can say the limit of the quotient is the quotient of the limit. So here are three easier ways to remember them. Limit of sum, limit of product, and limit of quotient. Lastly, we'll want to talk about continuity. So what does it mean for a function to be continuous? If a function f is continuous at a point x equal to a, then fx must be defined at this point and the limit must be equal to the real value of the function. Or you can say the limit of fx at when x is approaching to a is equal to fa. The function is discontinuous at a point if it's not continuous. Yeah, I think that makes sense. So that's all for today. We go through Chapter 17 summary. Hope this will help you. Thanks for listening.